Hi, my name is Rasika, and I'll be presenting on mitigating adversarial text perturbation with my co-authors Mohammed, Anand, and Igor. So here are some examples of adversarial text perturbation. So this first example at the top, basically they've put spaces between the letters of the word share to avoid detection for basically trying to artificially inflate the engagement for their post. Similarly, here in the second example, they've added extra I's and E's to the word like, and also to other words in the post. This third example here, they've replaced the S and share with a $sign, and they've also added stars before. This last example down here at the bottom, it's like the first example, but they put periods between the letters instead of spaces. So these are all perturbations to avoid being detected for artificially inflating their engagement. Before I move on to addressing this, I want to have a quick note on ethics, because some communities use text perturbation to avoid detection for their personal safety, or so that they can, for example, conduct journalism in certain locations. So, I encourage everyone to consider what their algorithm will be used for. Okay, so here are some common perturbation types that we compiled. So basically this one at the top, combined Unicode, is where we put any Unicode character between the letters of a word. So here we've alternated a period between each letter of please, like, and share. You can see that space separation is combined Unicode where the character is a space. In the example, you can see like and share, they've got spaces between them. And then also similarly down here, 0 with space separation is where the Unicode character is the 0 with space. And so that looks the same to a human, but it looks different to a computer. So those are 3 of the perturbation types. And then there's also fake punctuation, where they insert punctuation within a word. This is not alternating, it's just randomly inserted. And similar to that is random spaces, where they've randomly inserted spaces into the words, not alternating. And so yeah, and basically those are 2 that have things inserted into them. There's also other ones like neighboring key here, where this is often a typo, where a letter is replaced with something that's next to it on the keyboard. So here, W is close to E. There's also replace Unicode, where characters are replaced with Unicode characters that look like them. So here you can, to a human, we can see it says please, like, and share, but a computer will say, oh, the E is different from E with the hat, so it looks different. Similar to replace Unicode is tandem character obfuscation, where a character is replaced with multiple characters that together look like the original character. So in all caps, please, like, and share, but the A's are replaced with // and so that looks like, to a human, we can kind of read that, but a computer, it looks different. Similar to the other one with a typo is transposition, where basically letters that are next to each other in the word are swapped. This is also often a typo, but it could also be done adversarially. And then last but not least, there's vowel repetition and deletion, where vowels in words are either multiplied or just removed. So here, please is PLS, and then there's extra E's added to like and share. So some of these you can see just simple string manipulation will work for a defense against them. So you can see combined Unicode and its variations. We can look for alternating characters in the words and then remove the alternating character. So similar to that, there's also Unicode canonicalization, where we have a mapping of different characters that look like other characters. And so we can replace the characters with replace them all with the same, original character, so that they all look the same. And this also works for tandem character obfuscation. We just have a mapping of multiple characters. So that was 2 of the defenses. You'll notice that there was a 3rd type of defense for the remaining perturbation types. That is continuous word-to-vec. And here you can see it's very similar to word-to-vec. So this part here with the embedding layer and the dense layer, that part is like word-to-vec. The difference is that the spelling vectors on the edge, those ones there are not one-hot encodings from the dictionary. Instead, they are spelling vectors. And we calculate that by first selecting a random subset of the vocabulary. And then the spelling vectors are calculated by measuring the similarity between the strings of that word and each word in this subset. So the string similarity is calculated using this expression up here. Basically, L is Levenshtein distance. So we basically turned, because that's distance, so we turned that into similarity using fractions. So down here are some examples of the spelling vectors. So here, if our subset of the vocabulary was this short subset here, then the vector for adversarial, which is adversarial except with swapped letters, we basically do this string similarity for adversarial and each word in the subset. And so you get this vector here. And similarly, relation is not in the subset, but it's not like a misspelled word or anything, but we still treat it the same. We just measure the string similarity between each word in the subset. And so these 2 vectors are examples of spelling vectors that we would pass in for word-to-vec here, which is trained the same way, like the words are within the context window in the text. And in order to go from a spelling vector to the continuous word-to-vec vector, we multiply it by the embedding layer. So that's very similar to what you do in word-to-vec, right? Because when you multiply the one-hot vector by the embedding layer, you get the vector. So that's how you get the continuous word-to-vec vector here too. So the idea is that words that have similar context, like they're within the same context, and words that have similar spelling will both have similar vectors. So here you can see we evaluated this method. So up here on the top, we've got the correlation between Levenshtein and cosine distances for words. So basically, as a baseline, we used fast text, and then our method is CW2V. And so we measured the Levenshtein distance between the texts of the word, and then the cosine distance between the vectors calculated using those methods, and found their correlation. So here there's, we evaluated this when the words that are tested are from Facebook, and also when they are from the dictionary. Of course, we trained these vectors using Facebook, because that's how you can get context windows. And so, we would expect it to do better on Facebook. It seems it does a little bit better on the English dictionary, but not far off. But you can see that CW2V is better than FastText because we intentionally trained it this way. Down here, we also evaluated basically if you perturb a word, does that change the vector more than just having a completely different word? So basically, we took the cosine distance between a word and a perturbed word, perturbed using each of these 4 column names, those 4 perturbations. So cosine distance between those divided by the average cosine distance between random words. So a smaller number is better here because it means that perturbation changes a vector less than just switching the word to a different word. You can see that we again have fast text as a baseline, and we also did this using Facebook posts and also using the English dictionary. And so bolded means that the number is smaller in this case. And so you can see when our method is affected less by perturbation and when fast text is affected less by perturbation. So that was just evaluating the vectors just like that. Here, because you're probably going to use these vectors for some downstream task. So here we tested it on an engagement bait classifier, essentially detecting those posts that we saw examples of in the first slide, where it's a classifier. It has engagement bait and then not engagement bait. So here you can see kind of the method that we used. The column 1 is where we trained the CW2V vectors themselves. We trained them using 40,000 Facebook posts, passed them through the string manipulations, tokenized and trained. 2 is where we took those CW2V vectors to train the classifier. And then we also, column 3 is where we used the classifier that was trained. So you can see exactly when we perturbed and put defenses into the pipeline. So here you can see how this table right here in the lower right, you can see how how our algorithm fares. So basically, when there's CW2V, that means that we used our method. ACD and UC are those string manipulation defenses. We, as baselines, we also included BERT with and without the string manipulations, and fast text with and without the manipulations, and also fast text trained on different corpus sizes. So, and then of course, at the bottom there, we have adversarially trained fast text, just as a comparison for what if you train it without any defense at all, because it includes the perturbations naturally in the text. So you can see the area under the ROC curve, plus or minus the standard deviation. Here you can see up in the right, you can see kind of the effect of spelling vector size, right? Like the size of that random subset of the vocabulary, how that affects the area under the curve. And so you can see, the spelling vector size, and then also how the embedding size in the word to vec, that embedding size, and then also the window size for the context, the size of the window, that 2 words would be considered the same context. So that's our method. Future work, of course, would include better addressing split words, because right now each piece of the word gets its own word vector. And so if there was some way to address this, of course, we could do the very computationally complex thing where we try every single possible place where you could put the space or remove the space. Of course, that is very complex and would take a long time. Another avenue for future work would be to allow trade-off between semantic and spelling distances. If you prioritize one over the other, that would be nice. And then of course, computational complexity, because right now this algorithm already takes quite some time just to calculate the string similarity between each parent and whatnot. So, this is how I would like to see where the work goes. I look forward to hearing what your thoughts are. Thanks.